Einstein then starts solving this Navier Stokes equation that we have found in the previous video with the boundary conditions that we have also laid out in the previous video, namely that the velocity should vanish at infinity and it should also vanish on the sphere. So at rho equal to capital R, the radius of the sphere. And we defined the rho previously. It is given by the square root of xi squared plus eta squared plus zeta squared. And therefore, let's rewrite this equation in the three components. So we have dp dxi equal to k. Then here we have the Laplacian of u, the first component of the velocity. The Laplacian is simply this operator here, del squared dxi squared plus del squared d eta squared plus d squared d zeta squared. And then we have dp d eta equal to k del squared v, dp d zeta equal to k del squared w. And we also have the condition that the divergence of the velocity is equal to 0, meaning that du xi plus dv d eta plus dw d zeta is equal to 0, like this. From these equations, it is quite easy to infer that the Laplacian of the pressure is equal to 0. How do we see that? Well, it's simple, because the Laplacian of the pressure is del squared p d xi squared plus del squared p d eta squared plus d squared p d zeta squared, which is equal to, if we use this set of equations here, k del squared du dxi plus dv d eta plus dw d zeta. But this is 0, and therefore we have found that this is actually 0. Now we have to start calculations to obtain the velocity and the pressure. So we have four functions to calculate: u, v, w, and p, pressure. At this point, Einstein defines a function v bar. We call it v bar. Einstein defines it as capital V, but I don't want to get confused with the y component of the velocity, so we will call it v bar. V bar is defined such that its Laplacian multiplied by the constant k, the viscosity, is equal to pressure. This is a definition, okay? Definition. We have defined a function v bar such that this is the relation between p and v bar. And now, if we take the derivative of the pressure with respect to xi, this is equal to k del squared dv bar dxi, and this is also equal to, if we use this equation here, this is equal to k del squared u. And if we take a look at this equation, we can define u as the derivative of v with respect to xi, and Einstein also puts another function u prime here, and of course, for this to be true, we have to ensure that the Laplacian of u prime is equal to 0, because this equation tells us that the Laplacian of the derivative of v bar should be equal to the Laplacian of u, and if the Laplacian of u prime is equal to 0, this equation is also satisfied. Then, similarly, for the other two components, we define v equal to dv bar d eta plus v prime, and also similarly we have w equal to dv bar d zeta plus w prime, and we have del squared v prime equal to 0, del squared w prime equal to 0. Now, if we consider du dxi plus dv d era plus dw d0, which is the divergence of the velocity, using the equations that we found above, we have del squared vw plus du prime dxi plus dv prime d era plus dw prime d0 equal to 0, because this is also 0. And we can rewrite this as minus du prime dxi plus dv prime d era plus dw prime d0 equal to del squared v bar. This is also equal to p over k. Now, without looking at the previous expressions that we derived, if we just concentrate on this expression here, we can choose for u prime this expression, u prime equal to minus derivative of v bar with respect to xi. This will help us find the solution, but do not concentrate on the equations that we found earlier, because if you check this definition here and you go back here, for example, if you substitute the expression that we defined for u prime in here, we would get u equal to 0. So that's nothing meaningful. But you will see that with these steps, this will allow us to find the expression for u. So we have to change something in the expression for u, and similarly for v and w, because if we use this definition here, well, you can understand that there's something fishy, because we cannot get the value u equal to 0. You will see the ingenious way through which Einstein solved this problem. Now let's move on. We have also v prime equal to minus dv bar d era, w prime equal to minus dv bar d0. So this is similar, okay? Remember that we have to solve the equation del squared p equal to 0 also. Now we have to do some calculations. We have to calculate the gradient of rho. This will be useful. This will be useful to solve our problem. The gradient of rho. What is rho? Do you remember what rho is? Rho is the square root of xi squared plus era squared plus 0 squared. So in polar coordinates, this is like a radial distance. And if you take this gradient, you will simply obtain the vector xi era 0 divided by rho. So you can also calculate the Laplacian of rho. This will be also useful. Laplacian of rho is equal to the gradient, or actually the divergence of the gradient of rho. So this is the divergence of the vector that we just calculated, xi era 0 divided by rho. And this is equal to, if you take the divergence, it's quite easy. First, you take the derivatives of this vector here. So you have the derivative of xi with respect to xi, the derivative of era with respect to era, and so on and so forth. So you get 3 divided by rho. But you also get derivatives of this denominator. So you get minus xi squared plus era squared plus 0 squared divided by rho cubed. This is a simple calculation. And then you have that this is equal to rho squared. So all in all, you get 2 divided by rho. Then we will also need the Laplacian of 1 over rho, which is equal to the gradient of the divergence of 1 over rho, which is equal to the divergence of minus xi era zeta divided by rho cubed, and this is equal to minus 3 over rho cubed plus 3 xi squared plus era squared plus zeta squared divided by rho to the 5th power, and this is equal to 0 because here we have rho squared, so if you check, that's 0. Now from here you can see that the Laplacian of 1 over rho is equal to 0, and also the Laplacian of rho is proportional to 1 over rho. So this means that del squared of del squared rho is equal to 0 for what we just found. And we can define now a function p0 divided by the constant k. This function p0 is related to pressure, but it is not the final solution. P0 is a function of rho. We will define it as a constant plus another constant, a plus c del squared rho. And we can also rewrite it as del squared a xi squared over 2 plus c rho plus b over rho. We can also rewrite it in this form because the Laplacian of this is 0, whereas the Laplacian of 0 can also be written as c times the Laplacian of rho. And we have found that the Laplacian of p0 divided by k is 0 because the Laplacian of a constant is 0 and the Laplacian of this is also 0 for what we found here. So this is a solution because p0 written in this form is a solution to our problem, because remember that we want to find the Laplacian of pressure equal to 0. This is what we want to solve. And also we can find other solutions, because if you consider, for example, the function f of rho equal to derivative with respect to xi of p0 of rho over k, well, the Laplacian of f will also be equal to 0, because this can also be written as d over d xi Laplacian of p0 over k, which is 0. So also derivatives of this function p0 over k are solutions, and what Einstein will choose to carry out all the calculation are solutions of the second order. We will see that we will be able to solve our problem if we choose these types of solutions, because they will comply with the boundary conditions. So this is the key part of the paper, the key idea to understand in order to fully grasp the concepts explained by Einstein in this article. So P0 is equal to K Laplacian of A xi squared over 2 plus C rho plus B over rho. And we can define this, the content of the Laplacian, as V0 bar, let's say. Remember that we initially wrote the problem as P equal to K del squared V bar. This is where we started. And then we made some calculations and we arrived at this point. We have not really found P and V bar, but we have found P0 and V0 bar. So they are two different functions, but they will help us solve our problem. So V0 is this function here. And now we will choose another function, the second order. So let's choose the second order. I will call it PE over K. So PE, the subscript E stands for Einstein, because this is the, let's say, intellectual work by Einstein. So far, this part was also found in the literature, in previous works. So even before Einstein, this was something known, a method known because it was contained in one of Kirchhoff's articles. And this article was referenced in Einstein's paper. But anyway, let's define PE over K as the second derivative with respect to xi squared of P0 over K. So this is the second derivative, not just the first derivative as in this case, but Einstein chooses the second derivative. So not really the first derivative, but the second derivative. We know that the Laplacian of this function, which is equal to this function here, is still equal to 0. And we will define P0 over K as del squared V0 bar, as we know. And this is equal to, if you also take a look at the expression for V0 bar, 2c del squared the xi squared 1 over rho, and we will define this as del squared v bar e, because we want this form. Pe is related to ve bar in the same way p0 is related to v bar 0, and p is related to v bar. From here, we can also see that we can also define actually ve bar as del squared v0 bar over the xi squared. And now we will assume that u prime is not equal to 0, v prime is equal to 0, and w prime is equal to 0. We will make this assumption, just like Einstein did, simply because we can use superposition. So we will find the most general expressions by using superposition. So first we assume that u prime is the only non-zero component of the velocity, and the others are 0, and then we will assume that the second component of the velocity will be non-zero, so v prime, and the others 0, and finally w prime will be non-zero and the others 0. So by superposition we can find the most general expression. Now in this condition we have Pe over K equal to del squared v bar E, which is equal to, now this must also be equal to minus derivative of u prime with respect to xi minus derivative of v prime with respect to eta minus derivative of w prime with respect to zeta. Why is this? Well, you simply have to remember some previous steps. The relations are here. We started from here, where we had P and V bar, but we have to assume that this is also satisfied by P0, V0 bar and PE and VE bar, because they must be solutions. So we will find solutions, and if they are solutions, that they must comply with this equation here. And in our current case under investigation, since v prime is equal to 0 and w prime is equal to 0, we get this simplified equation, and del squared ve bar is equal to 2c del squared dxi squared 1 over rho, like this. And this last equation comes from here, this last equality. And now if we take a look at this part of the equation, we have minus du prime dxi equal to 2c del squared dxi squared 1 over rho. And we will choose u prime equal to minus d over dxi of 2c over rho. And we will continue next time.